Okay, so now it's a pleasure to be able to introduce Søren finally. We'll tell us about generation conjecture for regular graphs.
Thank you, Jack. Yes, so I decided to speak about 8 different things at the same time. This may be unwise, but I'll try to be very systematic with my use of time, so I can make it to the end. Otherwise, it's going to be weird. So I hope I can make it through. So this doesn't help you very much, but I want to talk about something that we usually call the XYZ project. It sounds like a kind of a code name, but it actually means something. So let me start by explaining what I mean by this. And for this, I need to repeat some things that have, I think, all of them already been said during the conference. So, but I just want to make sure that we all agree on notation and so on. My graphs are always countable, and most of the time they will only have finitely many vertices, even though sometimes I'm okay with infinitely many edges. I will single out the sinks and the infinite emitters as special in this sense. This reveals what the convention that I'm going to use will be. And I will say that a vertex in a graph is singular if it's a sink or an infinite emitter. I will say that it's regular if it's not singular, and I will say that the graph is regular when all the vertices are regular. So at the bottom here, I have an example of something which is not a regular graph. There is an infinite emitter to the left, and there's a sink to the right. Now, when you have a graph, you can define a graph C-star algebra. This is defined by some generators and relations, a universal C-star algebra given by some generators and relations. And it's easy to see that you get a unital C-star algebra precisely when you have finitely many vertices. And I have only something to say about unital C-star algebras in this setting, so all my graphs will have finitely many vertices. And the relations, you know, they are sort of trying to encode the information in the graph, the sort of geometric information in the graph in a C-star algebraic way. And of course, this definition is somewhat hard to take in, but it's trust me, it's the right thing, and it goes back to the early work of Kunz and Krieger around 1980. So I want to work almost exclusively during the talk with regular graphs. So this means that the rule here, where I say for every regular vertex in the third axiom down here, that's automatically fulfilled. So I will always have that PV is the sum of the SE stars in this setting. And actually, when you know this, you can forget the second axiom. So you only need the second axiom in the non-regular case, but I put it in for completeness. So it's a key observation for everything I'm going to say that graph algebra is not just a C-star algebra, it's naturally a C-star algebra with at least 2 extra kinds of structure. There is a gauge action, which you get by putting a modulus 1 complex number on all the partial isometries and leaving the projections be. So you sort of tweak the edges, but leave the vertices be. This will give you, from the universal property, an action of the circle. And there's also a diagonal, which is a commutative subalgebra that you get by taking all the S alpha star. So by alpha, I mean a path, and the S alpha then is the product of S first edge times S second edge, and so on. It follows from the axioms. This is a commutative C-star algebra, and you can also check that it sits inside the fixed point algebra of the gauge action, just because when you're acting with the gauge action, you're sort of multiplying on a Z on each partial isometry, and you multiply on by a Z inverse on the star, and then this will simply cancel out in these examples. So I want to define 8 different notions of isomorphism, and I will give them these weird names. I will call them X, Y, Z isomorphisms. And here's the notation. I've been working with this for a very long time, so it's sort of second nature to me, but I realize it's not very natural. So I will remind you once in a while what this means. But it's sort of two definitions in one. So I sort of have 3 bits or like switches that you can think of. One is called X, and that determines if I want to have an on-the-nose isomorphism or a stable isomorphism. So if you see a 1 at the beginning of an XYZ, that means that this is an on-the-nose isomorphism. If you see a 0, it means that I stabilize, and then I have an isomorphism. So this becomes real equivalence in the cases that we care about. And then I will keep track of whether or not my isomorphism or stable isomorphism preserves this data, the data that I've put in my gauge action and in my diagonal. Right, so I will write y equals 1. This means that my isomorphism has to commute with the gauge action. And if I'm stabilizing already, I also have to stabilize the gauge action. So this is how we do this. If the last entry, the last bit, the set is 1, this means that the diagonal is sent to the diagonal. Or if you stabilize, then the diagonal tensor, the standard diagonal of the compacts, will be sent back to itself. So really what this means, and the best way to think about this, is in like a cube. So I have these 8 kinds of isomorphism. You can see up here, I'm trying to remind you what the order of the X, Y, Z is. So the first one, is it exact? The second, does it commute with the gauge action? And the third, does it respect the diagonal? And then you can sort of think of this as a cube. Down here, I just have ordinary stable isomorphism of graph algebras. And up here, I have on-the-nose, gauge invariant, and diagonal preserving isomorphism, right? So you have 8 different ways of doing this. And of course, these will be more or less related. And this is really the subject of my talk and the whole purpose of this project, which I have been working on for several years now with Efren Ruiz. So all that you'll see, if I haven't specified otherwise, it's a joint result with Efren. And there's sort of 4 things that you might want to do. You would like to maybe understand in terms of the graph in a nice geometric way what it means that 2 graph C-star algebras are isomorphic in the appropriate sense. So I'm sort of asking, suppose that I know that 2 graph algebras are isomorphic in a way preserving some, maybe not all of this extra structure, then how can you explain this at the geometric level of the graph? So this is the first type of goal. Second type of goal is to connect to dynamics, to symbolic dynamics. This is very close to the starting point of the work of Kunz and Krieger, where they really pointed out that there's a strong connection here, which is very important. Also, you would like to have classification, find complete invariance, and maybe even show that these kinds of isomorphisms are decidable in the sense that you could, at least in principle, perhaps, find an algorithm that will take the data describing 2 graphs and then simply spit out the answer, are they appropriately isomorphic? So this is sort of the big sort of project. And I might as well tell you right away that this is not something that I'm able to do. So I have a kind of a report card. I will do this after every case that I go through. And the only one that I'm completely satisfied with is the 001. And there I'm giving myself full grades. But otherwise, it's going to be a little sort of iffy. The last column here is the number of minutes I have to talk about every single type of isomorphism. It sums up to 47. And I'm already a little bit behind, so I need to be not too slow, but still, just interrupt me if you have any questions. Okay, so first I want to talk about, so I'm going through them in the order which is not really the natural order historically or even sort of mathematically, So I think this is the best order of explaining the ideas and where they come from. So it's sort of a pedagogical choice of ordering. And I'm going to talk about the 0, 1, 1 and the 1, 1, 1 case just after each other. So first of all, in order to be more precise about what I mean about connecting to dynamics, I should tell you what kind of dynamics I have in mind. Right? So the idea is that I have a graph, and this graph will always be regular, and it's going to be finite. So there are no infinite emitters, obviously, but also there are no sinks. And so whenever you have such a graph, then you can define a dynamical system. Dynamical system is just a doubly infinite sequence of edges in the graph. So what you should, and then the condition is that edge number n ends the place that edge number n plus 1 starts. So really the way to think about it is that it's xe is the set of all the infinite paths that you can get by running around on the graph. And you can very easily put a topology on this. You take the discrete topology on the edges, and then you take the product topology from this. This is a compact set. And then you can take a shift map that just takes all your paths. They're by infinite, so I can shift them one to the left or right and still have a path. So this becomes a homomorphism. And so you get a dynamical system this way. This is called a shift of finite type, and it's an example of a symbolic dynamical system. So it's a very sort of simple-minded type of topological dynamical system. And then the most natural way of saying that two such things are the same, which is called conjugacy, is to have a homomorphism between them, which commutes with the shift, right? So it preserves the topology, and it also respects the shift map. And so, of course, it's a natural question to sort of say, when do you get the same dynamical system this way, and is it at all related to the isomorphism of the C-star algebras? Now, before I go into this, we need to talk a little bit about essentiality, because I'm not going to require that my graphs are essential, and this is a normal thing to do in dynamics. So let me just say a few words about this. So we will say that the essential part of a regular graph is what you get by deleting all the sources, right? So if here's a graph which is not essential, because, for instance, there's a source out here to the right, and there's also a source out here to the left. And then what you can see, first of all, is that these sources will not contribute to the shift space at all, because the shift space are by infinite sequences. So since there's no way, if I start over here, there's nothing coming before it, so it doesn't even exist inside xe, which is this has to be doubly infinite sequences. So it doesn't really matter if there's a source or not. It doesn't play a role for the dynamics. Nevertheless, for the C-star algebras, we need to sort of deal with it. So this is what we're going to do. But what you usually do in dynamics is that you just pass to the essential part of the graph, which you just get by deleting all the sources, right? And you may have to do this repeatedly, because, of course, over here, this is not a source, but when I've removed this source, and it becomes a source. So I also have to remove this. So the essential part in this particular case is just what you see down here, right? And obviously, the shift space associated with a graph is the same as the shift spaces associated with the essential part of the graph. So it's common in dynamics to just put in the condition that the graphs are essential. Usually you say no sinks or sources. I mean, I've ruled out the sinks already because it's a regular graph. So this is what I'm doing with essentiality. And then there's a very nice result, which is really the starting point of this whole project. When we saw this, we got very excited and tried to sort of put it in a bigger framework. It's a result which is about 10 years old by Tuve Carlsen and James Rout. And they proved that actually two essential graphs will give you the same dynamical system. They will be conjugate if and only if the graph algebras are 0, 1, 1, right? And what does 0, 1, 1 mean? It means not exact, so it's a stable isomorphism, but it respects the gauge action, and it respects the diagonal. So this is an amazing result. It sort of says it's a rigidity result. It sort of says that all you need to know about the dynamical system is stored in the graph C-star algebra. This is a special case of this is a conjecture algebra. But you cannot work with the algebra alone. You also have to keep track of the gauge action and the diagonal. So now I would like to use this to give you a geometric description of what's going on. And fortunately, there's a very strong result in the literature going back to the work of Williams, understanding conjugacy among shifts of finite type. And he came up with a way of changing the graph without changing the dynamics. And this is called outsplitting and insplitting. So an outsplitting, I mean, there's a formal definition, of course, but I think it's easier to understand if we just take an example. We take a graph, a regular graph, say, and then at some point we find a vertex that emits more than one edge. And then we take the set of edges that is emitted, and then we subdivide it into a finite number of non-empty sets. So we take a partition, and then what we do, and in this particular case, I took the loop and the topmost edge across and put in the first set of the partition, and I took the lower edge of the, across and put in the second set of the partition. And then what you do in the outsplitting is that you take the vertex and you split it into more than one vertex, and you simply distribute the edges out in the partition, one for each vertex. So I had two sets in my partition, the topmost and the one in the top, the two at the top, and I put it over here in one of my new vertices, and I have this one and that one as you'd expect. And then the second one I have down here and put it across. And then the point, of course, is, you know, now I told you what to do with the outgoing edges, but I haven't told you what to do with the incoming edges. And the rule for incoming edges, and this is where this becomes a little bit tricky, and it's a very interesting construction that Williams came up with, is that you duplicate the incoming edges. And then when you have a loop, of course, a loop is simultaneously an incoming and an outgoing edge. Then the rule is that you need to sort of, when you distribute it, it always emits from the vertex that is the chosen one for this particular loop, but it's also duplicated as an incoming edge. So that's why this loop here gives me both this one and this one in the definition. And now it's fairly easy to see this sort of follows more or less by the definition. This was seen by early work of Bates and Pask, that when you outsplit a graph, you're not changing the C-star algebra at all. So it's a 1-1-1 isomorphism. So this is what I mean by invariance. So it's an on-the-nose isomorphism that sends the gauge action to the gauge action and the diagonal to the diagonal. So as nice as you could hope for. But it turns out that when you sort of do the opposite way, and this is completely dual in the classical case of that Williams was interested in, but when you pass to the C-star algebras, it's not symmetric anymore. And actually you get a 0-1-1 isomorphism this way. So you will only get a stable isomorphism. You will change, in a sense, you'll change the class of the unit in the K0 group. You will sort of have to do this, and this will make an isomorphism which is not on the nose, but it will actually preserve the gauge action as well as the diagonal. So this you can do both in dynamics and in C-star algebras. And then if you sort of put these things together, if you're in the regular essential situation and you combine these two results, you can see that you will get 0-1-1 isomorphism if and only if you have conjugacy, if and only if E and F are in, and this is what this bracket means, in the smallest equivalence relation containing O and I. And I'm super interested in the equivalence between 1 and 3, and this, in a sense, is the generation question that I'm addressing in the title of the talk. But of course, the second thing in the middle is sort of interpolating and is closely related to the dynamics. So this is also important. But you can see this. So this is a sort of an explanation of what is 0-1-1. But you can see it's only for the essential graph. So we have a little problem dealing with the sources. And what you usually do is that you come up with another move, another way of changing your graph, called an S move, which is simply that you plug in, you can put an extra source somewhere in your graph. And then something somewhat surprising happened. Actually, this is something that I only realized about a year ago, that this is always true in the regular case, because when you sort of check this, what an S move does to your graph, it's very easy to, first of all, you can see it's almost never an exact isomorphism you have to stabilize. It's very easy to see that the diagonal will be preserved, but you don't expect it to preserve the gauge action. But it actually turns out that if you, and this is also for a general graph, not necessarily regular, this is also as good as it gets. But actually in the regular case, it is promoted to a 0-1-1 move. So actually when you do an S move on your regular graph, it will not only be 0-0-1, it will be 0-1-1. And of course, this means that you can sort of throw it in. It's invariant enough that you can think about it in a 0-1-1 condition. And now this is a result not for essential graphs, but for all graphs. Right? So you can sort of generate by O and I and S. This in a sense is very nice, but actually there's an even better way of doing it, and that's actually also how we prove this specialized invariance. Let me explain this, because it's a better way of thinking about this, and that is, it turns out that actually in splitting, you should allow yourself empty sets in the partition. And this is a bit weird, right? This is not something that dynamicists would sort of find natural, but from a C-star algebra point of view, it's very natural. So what you can do is, if say that you're in splitting here, right? So this means that I take all the incoming edges and I need to partition them. But this time I decide to partition them with all 3 incoming edges in one set, and then I have another set that's empty. And then the rule is that I should then have 2 vertices, and you sort of distribute the incoming edges and you duplicate the outgoing edges. So then you get something like this, which means that I've sort of introduced a new source, but it's in a controlled way. It's super easy to see that this I minus move is 0-1-1. But what is not so easy to see, and this is something that took us a while to understand, is actually you can take this source addition move and you can generate it by O and I minus in the regular case, not always, right? So in the regular case, you can always do this, and I can give you an idea of how this goes. For instance, taking this source, I could remove it using an S move in reverse. But actually, it's also very easy to get it from an I minus. If I just take this vertex and I take the incoming edge, there's only one incoming edge that comes from the loop. And then if I just make a partition with that and an empty set, I will exactly introduce this thing here. So you can sort of see that an S move in this particular case, I can get with an I minus move. So here, this is a little bit more complicated, but actually what you can do is that you can start looking over here, and you can say, okay, what happens if I I minus this vertex? Well, there's only one thing coming in. So when I minus it, I will get a new source that sort of ends over here. But then you can see that this is actually, this then has the same future as this. So you can actually use this to get rid of the other thing. So you can really sort of unravel these sources using the O and I minus move. So this means that this S move that I just defined for you, and which turns out to be important in general, if you have a not necessarily regular graph, it's redundant here. So you can forget about it. And this, I think, is the best way of formulating it. So I'm just calling it, this is my 0-1-1 theorem. For regular graphs, they will give you the same C-star algebra, stably preserving the diagonal, preserving the gauge action, if and only if the dynamical systems are conjugate, if and only if you can go from E to F using these moves O and I minus. So my report card is, I'm going to give myself marks for a geometric interpretation, because I can sort of tell you what it means to be 0-1-1 in terms of, this means that I can take one graph and I can use O and I minus a number of times, finite number of times, and then I end up in the other graph. There's a strong connection to dynamics, but I'm not getting any points for complete invariance or decidability, right? I haven't been able to say anything about this, but actually what I can tell you is that this is a famous problem in symbolic dynamics to figure out if conjugacy is a decidable property, and if, which I guess would be necessary to come up with some sort of complete invariance. So, I cannot solve this, but a lot of experts in dynamics also cannot solve this. So I guess that helps a little bit. So if you want to do the 1-1-1 case, so where everything is preserved, then you really need to think about the one-sided shift space. So it turns out that, in dynamics, of course, a two-sided shift space is much nicer because then you have an inverse to your shift. But the more natural thing to look for when you're having on the nose isomorphism of C-star algebras is the one-sided shift space, where I'm simply I'm not taking bi-infinite sequences, but just standard infinite sequences. And then there's an obvious notion of conjugacy, and there's also something called eventually conjugate shift spaces defined by Matsumoto. This is related to some of the things that Kevin talked about on the first day. It's a little bit, it's an orbit equivalence, which is nice in a particular way. The notation is a little bit problematic because eventually conjugate means something else in other contexts, but I'm just going to use the notation that Matsumoto used, right? So the question is, these two concepts, are they the same? And if not, which one of them is the one that is relevant for what we're doing here? And so Matsumoto defined this in a paper quite a while ago, and he was sort of floating the idea that actually eventual conjugacy would be the same as conjugacy. And he proved that 1-1-1 is the same as being eventually conjugate. He proved it in the special case giving a simple C-star algebra, and this was then generalized by Kevin and Tuka Carlson. But when you compare this with conjugacy, then Williams, this is a classical result, shows that actually the smallest equivalence relation generated by just outsplitting is precisely what generates conjugacy. And then there was this example by Kevin and Tuka, which explains that these two graphs that you see there, they will give you the same C-star algebra in any reasonable sense, preserving the gauge action, preserving the diagonal, and so on. But they are not something that you can go from one to the other using outsplits only, and which is easy to see from the setup. So this tells you that actually these concepts have to be different, and it's the eventually conjugate one that is relevant for what we're doing here. And then you can also look at what is conjugacy. This was the subject of Kevin's talk on Monday. So I'm sort of going in the opposite direction here. But then when you sort of stare at this, it's really very easy to see what you need to do in order to do this by moves. So we came up with this idea of an I plus move, which is sort of, so the notation is I have I, which is the standard in splitting. I minus is a generalization of that. And now I make a specialization of the I minus and I get I plus. And the way it works is that this is just like an I minus. I start from the beginning and I make an in-splitting of a vertex, right? So in this case, this vertex here. And I do it in two different ways, but I have the same number of sets in my partition. My partition is allowed to be empty, allowed to contain empty sets. So really, I could take this one here and I can go to the left, which is what I did when I showed you the I move. I can go to the right, which is what I did when I showed you the I minus move. And then the point is that when you sort of cut out the middleman and just compare the ones on the sides, they will actually give you something that's 1-1-1. So the problem, the thing that gives you a stable isomorphism and not an on-the-nose isomorphism, is precisely when you have a different number of sets in your partition. So the way this works is that, so the definition is that you take the gray graph that I have in the middle, and then I will say an I plus move I get by making two different I minus moves. And then the I plus relation is between the the extreme ones, right? So they're not I plus to the one in the middle, but they're I plus to each other. There's perhaps a better way of explaining it, is that whenever, if you have a situation where you have two vertices that have exactly the same future, so you can go to exactly the same places with the same multiplicity, then you're free to sort of redistribute the past. This is really what I'm doing. So when you have this, then you can prove this is actually a little bit harder. We've done it. That this is a 1-1-1 move, and then Kevin proved very satisfying result that if you have regular graphs, they will be 1-1-1 if and only if you have eventual conjugacy, if and only if they are generated by O and I plus. And the report card, then I would say, it's a strong connection to dynamics. There's a nice geometric description, but we have no complete invariance. We have no clue about decidability. And this is very frustrating. This is something that Kevin thought a lot about, because actually it turns out that one-sided conjugacy is decidable. It's very easy to decide. So, and this feels very close. So somehow you would hope that you could do better here than in the classical two-sided case. But this hasn't happened yet, and maybe it's just impossible. I don't know. So so this is what I had to say about the X11 cases. Okay, I'm pressing on to the 001. So 001 is the one that is most satisfying here. I have a very precise result that I can show you. And it goes via the notion of flow equivalence. And this may not be something that you've seen before, but it's sort of a standard thing in dynamics. It goes back to some old work from Hedlund in the 30s, I believe. So there's something called a suspension flow, where you sort of take your shift space and you cross on a line, and then you identify the element x comma t, where x is in the shift space and t is a time parameter. You identify x comma t with the shift of x comma t minus 1. So it's just sort of a standard condition of taking a set dynamical system and making an R dynamical system out of that. And then you can define x to be flow equivalent to y for two such shift spaces if these suspension flows are isomorphic, homomorphic in a way that doesn't change the order that you have in the real lines. This makes sense, but actually the reason why I care about this is that it has a nice sort of move description. And what you want to do is that, so the whole idea of a flow equivalence is that you're somehow distorting time. And the way that you can distort time is to take a vertex. If you have a vertex in your graph somewhere which does not support a loop, then you can sort of delete it by just saying that whenever you had a path that went through this vertex, you just replace it, the indirect sort of two-step path, with a one-step path, right? So instead of going from here to here in 2 steps, I will just sort of skip over the star. This only makes sense if you have no loops. So this is why I have this in my definition. And it's easy to see that this is a 001, right? So 001 means it's a stable isomorphism. It does not commute with the gauge action, but it does set the diagonal to the diagonal. Okay, so Kevin says, yeah, that's right. Okay, so Carlson-Rauch did the isomorphism. Kevin is protesting he gets too much credit, but so Kevin showed the generation result, which is the most interesting thing for me here. But I guess you're right. So the point that I'm trying to make here is this is a way of changing the graph, and it turns out to fit very nicely with the general questions that we're talking about. So it turns out this is a result by Perry and Sullivan, and it is the Sullivan, that two shift spaces are flow equivalent if and only if E and F is in the smallest equivalence relation generated by conjugacy and this R move. So since we know that conjugacy is generated by O and I, it's the same as saying that EF is in the smallest equivalence relation generated by O and I and R. But they also showed that that this and this was sort of formalized in work by Bowen and Franks, that you can take two graphs. So the most obvious choice is this one and this one, and you will get two graphs that are not flow equivalent, even though they have the same. There's a natural invariant, which is a co-kernel of a certain matrix. It turns out to actually be the same as the K0 group of the Kunz-Krieger algebra. And it turns out that this is not enough information. You need to look at a special sign of a determinant. This is related to the question that I asked Bishan after his talk. So in order to get flow equivalence, you need more information than just the K-theory. And then Kunz observed very early on that it was hard to prove that if you take these two graphs, it was hard to prove that the C-star algebras were different, even though the underlying dynamics was different. And actually, Rørdam then proved that actually they're the same, right? So this means that the C-star algebra in itself, the 001 equivalence, is too weak to really keep track of flow equivalence. And the solution, and then this took decades before we learned this. This was done in work of Matsumoto and Matsui in the simple case, and then I generalized it with Carlsen, Ortega, and Restov. Then that actually flow equivalence is the same as 001. So this is a very satisfying result, and we can do even better because it turns out that flow equivalence is a decidable property. So there's a procedure of figuring out when you have two graphs defining shift spaces this way. They need to be essential, but that's not really a big deal because you can just remove the non-essential part. And there's this condition here, which I don't really have time to explain exactly what it is, but what you have to do is that you sort of look for an intertwining matrix, intertwining pair of matrices. And then these matrices have to be in a special form. They sort of have to be block diagonal. And then they intertwine not the adjacency matrices of the graphs, but the adjacency matrices -1. And this is actually a very natural thing to look at from the point of view of the Bowen-Franks invariant, and this turns out to work. This is work by Boyle and Huang. But the point is that in order to even look for these matrices, which are square matrices, then you need to know that the adjacency matrices for E and F are of the same size. So you have to have the same number of vertices. In particular, actually need to have the same number of vertices in each component in the appropriate sense. So this is what standard form means. But it turns out that you can, in a canonical way, and well, maybe not canonical, in an algorithmic way, you can organize this. And then when you have sort of arranged things so they have the same size, then you just have to go looking for this matrix, which is block diagonal integer matrix, which has determinant 1 in all the diagonal components. And this, by work of Boyle and Steinberg, is actually something that there's a procedure for checking. So if you put all of this together, this is my 001 result, right? So this diagonal preserving, but otherwise not nice. 001 is the same as flow equivalence. It's the same as being generated by O, minus, and R. And it's decidable because you can do it with matrices, right? So everything works out here. So before I did the 011 at the same time as the 111, I have a good reason for waiting with the 010. No, with the 10. What am I trying to say? So we just did the 001. And of course, now there's the 101. But let me postpone this a little bit and talk first about the X00 case, right? So now I have the two cases where I either have just a stable isomorphism with no other structure, or I have an exact isomorphism with no other structure. And so in order to deal with this, now this is just sort of classification of C-star algebras because now there's no other structure. And it turns out that what you can then do is that you can sort of make two definitions. So the one definition, the so-called Kunz-Splice, is the one that's sort of necessitated by the example that I just showed you that goes back to Kunz. So if you have a vertex somewhere in your graph, that already supports two different ways of going from that vertex back to itself. This is an important technical condition. Then you can sort of glue this graph on. This is called a Kunstsplice. And it's easy to see that this will change the flow equivalence class of the C-star algebra. So it's not a 0-1-1 move. It's not a 0-0-1 move. But by the work of Rördam, which you need to generalize a little bit for this, it's a 0-0-0 move, right? So it does not change the C-star algebra. And then you have to do something similar in a more complicated situation. This is something that only happens if you have a vertex which has a unique loop on it. So if you have a vertex where you can sort of run around on it in a unique way, then you may have to come up with this kind of move. This is we call it a P move, the Pulelehua move. So it's named after a Hawaiian butterfly, because we did it in Hawaii and we think it looks a little bit like a butterfly. But it turns out that you can prove that this is a 0-0-0 move. So again, this is a way of changing the graph. It's sort of, I mean, it looks a little bit weird. It comes from K-theory, right? It's something that you do in order to change the K-theory in a way that you would like to do in a controlled manner. But then when you sort of do this, you get a 0-0-0 move. And then we have the 0-0-0 classification result, which is just a classification of these objects up to K-theory. We will say that they're 0-0-0 equivalent. If and only if you can go from one to the other using the three moves that I already talked about, O, I minus, and R. And then these two new moves, C and P. And in the general result, you have to throw in the source addition move. But since I'm talking about regular graphs here, it's redundant. I get them already from these two first ones here. And then it turns out that this is decidable using GL equivalence. So it's the same definition as before, but this time I only want my diagonal matrices to be invertible. So the determinant could be plus or minus 1. So this is a geometric interpretation of this, I would say. We have a completed variant. You can also phrase this using K-theory, but usually this is what I have here is easier. It's decidable, but there's no real good connection to dynamics. I mean, I've sort of been trying to I've shown this to dynamicists, hoping that they would say, oh yeah, this looks like blah, but I've never sort of been able to get any sort of response from dynamicists. So this, I think, is probably just an honestly C-star algebraic thing. So, and then you can, if this was 0-0-0, so if you want to do 1-0-0, then you just have to tweak your moves a little bit. So instead of making a standard Kunstsplice, you do a Kunstsplice with an extra source. Then you can see that actually you get an isomorphism on the nose, not just a stable isomorphism. And you can do something similar with a P move. You have a source down here. And you can even do something about the R move, right? So the R move is where I took a vertex and I deleted it. And it turns out that if you want an isomorphism that will give you not just a stable isomorphism preserving the diagonal, but an exact isomorphism preserving the diagonal, what you need to do is that you need to sort of keep this vertex as a source. So I sort of have it over here, but as a source. And now in this particular example, it just emitted one vertex, but if it would have been emitting more, I would just sort of take a carbon copy of that and put on sources. And then you can prove that R plus is a 101 move, and C plus and P plus is a 100 move. And then you can do the parallel result. This is something I did with Efren and Sarah Arklint, that you get 100 if and only if they're generated by these plus moves and O, which is always exact. And also there's a way of describing this in terms of matrices. So this time it has to be a matrix that sends the unit to the unit in certain K-theories. So there's an extra condition on the matrix that somehow makes it unit preserving. So again, we have a geometric interpretation, we have complete invariance, we have decidability. but we don't have a good connection to dynamics. Okay, so this is sort of what I had to say about the 5 first cases, and the 5 first cases are the ones that we understand, I would say, very well. I mean, so the things that we don't understand, these are things that are well-known open problems. But for the remaining 3 types of isomorphisms, there are things that I don't know. And actually, I'm giving this talk because I've been working with Efren on sort of improving our results. So we wrote a paper and we put it out a couple of years ago on the archive, where we sort of collected fairly easy things about this and proved all the invariants. But now we've sort of trying to go through this again and see if we can do more. And we haven't been very successful, I should say. We can do a little bit more, and I'm going to show you this in a second. But most of the things we're finding ourselves, we're not able to do this in complete generality, but at least I think I have a better understanding of why it is that I cannot do this. So this is really what I want to tell you for the remainder of the talk. So, but let me just recap what I've done this far, right? So I've shown you these 6 types of moves, and we've checked sort of how invariant they are, right? So all of them except I minus, they will be exact isomorphisms, and then some of them will preserve the gauge action, some of them will preserve the diagonal sort of in a mixed way. And then the generation conjecture is simply the idea that if I take this connection of moves, and then I just say, okay, let me take those moves that are invariant in an appropriate sense, and let me ask the question if these moves will generate the appropriate isomorphism, right? So this I have, for instance, for 0, 0, 0. If I take all the moves, I will get 0, 0, 0. And I have it for 0, 0, 1, I have it from 0, 1, 1. I have it for 1, 0, 0, and I have it for 1, 1, 1. Right? These are things that I already proved and mentioned. So for the remaining 3 cases, I sort of would like to do the same. And it will be obvious in a second that I'm going to have a new move in order to deal with the 0, 1, 0 and the 1, 1, 0 cases, because my moves that I've given you are not really fine enough to distinguish between 0, 0, 1 and 0, 1, 0 and 0, 1, 1 and 1, 1, 0 and 1, 1, 1. So I'm going to have to come up with a new move. But at least for the 1, 0, 1 case, we have a good candidate for what it should be. It should simply be those moves that are 101 invariant. So that's O, it's I plus, and it's R plus. Right. So this is what I would like to know. Now, if you sort of look at 101 in terms of rigidity, there is again important work by Matsumoto. Matsumoto defined something called continuous orbit equivalence, and then proved that actually this generates 101 isomorphism. And this he did in the simple case, and we generalized it with somewhat different methods to all regular graphs. So we have that the one-sided shift spaces are continuous orbit equivalent if and only if we have a 101 isomorphism. So that's an exact isomorphism that sends a diagonal to the diagonal. Now, we actually also have a kind of a description of when do E and F, when can I make F from E using only the moves O, I plus, and R plus. And this is what we called SL1 equivalent. So this is like, it's like the union of the 2 things I already showed you. I had something called GL1, which is a GL equivalence that sends unit to unit. I had something that's called SL, that is an SL equivalence. And then an SL1 is just one that has, determinant 1 down the diagonal, and it sends the unit to the unit. And we can prove, I have to phrase it in this sort of strange way in order not to lie to you. But so essentially what this means is that we have a kind of description of when can you go from E to F using only these 3 kinds of moves. And then if you're a little bit careful, you can you can solve this simple case this way, right? And I've been mentioning the simple case once in a while, but this is the first time I sort of need to really use it. So let me be careful here. I will say that, if I have a regular graph, the associated C-star algebra will only have trivial gauge invariant ideals precisely when the essential part is strongly connected. So what I mean by strongly connected, we've talked about this before at some point in the conference. It means that whenever I have two vertices, there's an edge, there's a path from one to the other, including from a vertex back to itself. And of course, this is never true for a source, but it turns out that the sources are not important here. So you can pass to the essential part, which in this case would be this part of the graph. And then you just need to check, can I go from every vertex to any other vertex in the essential part? Right? For this particular graph, the answer is no. There's no way I can go from this vertex here to this vertex here, for instance. So this will not give me a simple C-star algebra, gauge simple C-star algebra. But sometimes, of course, you get this. So if you stick to this case, there's a nice result that Efren and I proved. So 101 equivalence, thing number one here, is the same as continuous orbit equivalence. This we know is true in general. It's the same as being generated by O, I plus, and R plus, and it's the same as this SL condition. And the way we prove it is that we interpolate using this thing here, which is the intersection of 1, 0, 0 and 0, 0, 1. So this may look a little bit strange. So what this means is that E and F lies in the first equivalence relation. This means that there is an isomorphism that sends the unit to the unit. And it lies in 0, 0, 1. This means that there's an isomorphism on the stable one that sends a diagonal to the diagonal. This is weaker a priori than 101, because 101 is an isomorphism that does both, right? It's an exact isomorphism and it sends the diagonal to the diagonal. But in the simple case, we can show that it's the same, right? And then we have a relatively satisfying result. So parenthesis means that, check mark means that this is okay, but it's only in the simple case. And so this we've had for a long time, and I was just thinking it was a question of making our proofs a little bit better before we could generalize this to all graphs. But it turns out that there's a really strange phenomenon here that I'm just going to show you this pair of graphs and then move on, because I don't really know what to do about it. But here's an example. This is a rare, this doesn't happen very often, but we found these two graphs. They have the property that they give you the same C-star algebra. They give you the stabilized same C-star algebra, preserving the diagonal. It's actually, the difference is just this source down here, right? So you can see that the difference is just a source, and the source is a 0, 0, 1 move. So this is an example. These two graphs, they're 1, 0, 0, and they're 0, 0, 1. But we can prove that they're not SL1. So you can not go from one to the other using the moves. So this means that, something's got to give here, right? So either it's not true that 1, 0, 0 is the same as 0, 0, 1. That's what I think is probably not true, right? So it's probably not the case that these two things are 1, 0, 0, 1, 0, 1. But we're not able to disprove this, right? So we don't have the tools. The point is that, sometimes, the way that you do this, and this is contained in the work of Matsumoto and Matsui, is you need to deal with some determinants. And these graphs that I've chosen here, they have zero determinant, because they're invertible matrices. These, this irreducible component here will give you 1, 1, 1, 1 when you subtract 1, and this is an invertible matrix. So there is no determinant, and we don't know how to prove or disprove that these are the same in the 1, 0, 1 case. So this is why I cannot do this, right? This kind of example is what is keeping me back. Okay, so now it's 4 o'clock. Can I speak for about 7 minutes more and then take questions? Will that work?
Much, because we cheated you at the beginning, but
okay, that's great. Okay, I think I can make it this way. So, there's only two cases left, right? 0, 1, 0, and 1, 1, 0. And for this, you need to look at the fixed point algebra, right? So I mentioned at the very beginning that the fixed point algebra contains a diagonal. It turns out to always be a corner of a graph algebra, which is AF, and you can actually describe it as a corner of a graph algebra. So it's a little bit complicated. I mean, this is the first graph I showed you. This is a non-regular graph. There's something called the skew product, where you take the graph and you sort of repeat it infinitely often, and then you take the edges and you sort of make them point from instance number n to instance number n plus 1. So, I mean, this graph here is where, you know, I've taken the vertices and I've repeated them a number of times, I mean, and by infinite number of times, and then I take the edges and I make them point forward. So this will give you a graph algebra, and then it turns out that the fixed point algebra is a corner in this graph algebra. It's a graph algebra which is AF. So this was worked out by CRISP a long time ago. So really what you can see is that this graph algebra, it comes with a shift map, because I've repeated these things infinitely often. So I can just take one copy and move it to the right. This will give me a shift map. And using this, I can define two objects. And the first object I'm going to define is a classical thing. It's well known in symbolic dynamics. It's called dimension triple. It was introduced by Krieger. He was inspired by work in C-star algebras, but actually, you know, the way that people use it in dynamics, they wouldn't think about C-star algebras, but it is the K-theory of this AF algebra. So it's a dimension group. So it's a triple because I have you know, the group, I have an order on the group, and then I have the action of the shift. Right? So this is sort of a pure algebraic data that I'm keeping. And then the dimension quadruple is I throw in the class of that unit, the corner that I used to pull out the fixed point algebra. And then there is a classical result by Bradley Kishimoto's about it's from the turn of the century by Bradley and Kishimoto, which says that 0, 1, 0 isomorphism, so stable isomorphism commuting with the gauge action, is exactly the same as isomorphism of the dimension triples. And then by work of Krieger, this is the same as something called shift equivalence that I'm not going to define for you, but it's a notion that was introduced by Williams in order to understand conjugacy better. And then he actually thought they were the same, and he stated it in an annals paper that he then had to retract this particular statement. Kim and Rausch, sort of eminent dynamicist, they proved, first of all, that it's a decidable property. So there's a way of checking this thing, which is why Williams introduced it. But they also proved that actually Williams was wrong. So they found a pair of graphs. This is very deep. I mean, this took decades to do, that you can find two graphs that will give you shift equivalent systems. So 0, 1, 0 C-star algebras, but they're not conjugate, right? So using the Carlson-Rout result, they are not 0, 1, 1. So this means
Søren, can you explain what you mean by gauge simple C-star algebras?
I just mean no gauge invariant ideals except for 0 and everything.
Okay.
So, I mean, you can have a circle, right? So the circle algebra is not simple, but it's gauge simple. That's really all I worry about. And it turns out that this question, I mean, this dimension group, it's like a graded K-theory, and there's a big sort of body of work in Levitt path algebras led by Ruspe-Hasrat, where you sort of study this, and this is called the or a Hasrat conjecture, because there's actually two. This is his Morita equivalence conjecture that, you know, if you could prove this, then you could also do this more generally. I'm putting myself and Gabor Szabo in because actually, in order to prove what I have here, you need to look at dynamical systems that are irreducible and not just primitive, in case you know what this means. So this is a little subtlety that means that instead of getting the fixed point algebra to be a simple C-star algebra, it's a direct sum of simple C-star algebras. And this was not covered by the work of Bradley Kishimoto, which goes by, you know, Rocklin property, this kind of stuff. But if you're Gabor Sabor, it's fairly easy to generalize to this case. So this is what we did. And you can sort of do it unitally as well. This 110 becomes the same as the dimension quadruple. And there's a natural way of phrasing this, which was coined by Kevin, so I put him in as well. So this is the same as balance shift equivalence. And there's another Hasright conjecture that sort of says that if you could prove this, then you would have this in more generality. Now, I would like to do this with moves, right? And I've been trying to come up with a good move. And this is, in a sense, this is me sort of giving up. And then I will just say, there's a Krieger move. A Krieger move is I will say that one graph is, I can go from one graph to another using a K plus move if they have the same dimension quadruple. So this is cheating, right? This is not really a geometric way of doing it. But, you know, when you do this, then you can sort of take what we know and put it in a nice result in the same way as what I did before, right? So 0, 1, 0 is the same as shift equivalence, is the same as being generated by O, I minus, and Krieger move. So this is connected. Oops, I hear myself in a strange way now. Okay, it's better. So, I mean, I put minus on geometric because the K plus move is not a geometric move. But I get, you know, dynamics, I get complete invariance, I get decidability in the simple case. I have no idea of how to do it in general. And for the 110 case, it's the same, but actually there's no decidability result known. So this work of Kim and Rausch does not cover the on-the-nose isomorphism that I would need. And then my last slide is this one. So this is really the status, right? So this I tried to put everything on one slide. So maybe this is a little bit confusing, but let me explain. So I'm looking at regular graphs only. So all of my moves, I know how invariant they are, except for the Krieger move, right? So it actually turns out that the hard part for the Krieger move is to prove that it's gauge invariant. So this is really the hard case, and I can do it in the simple case using the work of Bradley and Kishimoto. And then for the generation results, I actually have them all in the simple case, right? So in all the simple situations, if I take the subset of moves that is appropriately invariant, then it actually generates the appropriate equivalence relation. And the way that I did these moves, I didn't talk about the non-regular case, but the way that you can just take these definitions and they will still make sense in the non-regular case. And I conjecture this will work there as well. I cannot prove it, but I also have no counterexamples. Okay, that's it.
So are there any questions?
Anybody on Zoom?
Anybody on Zoom have questions?
Well, I have a very simple-minded question. It's not directly related to your talk, but you mentioned it, and it's coming up at this meeting, so maybe we can explore it a little bit. This concept of strong connectivity, okay? And when you speak about the usual connectivity, then it has a very nice topological interpretation. It turns out that we can turn hereditary subsets into topology. So just declare that hereditary subsets form your topology, and the property of being hereditary allows you to do that. You can check it's a topology. And then lo and behold, it turns out that being connected in this topology is equivalent to being connected in the combinatorial sense. So I'm wondering if you have some non-combinatorial, really topological interpretation of strong connectedness. It's not a very deep or important question.
Yeah, I think, I mean, to me, it's always a question of keeping track of the ideal structure of the C-star algebra. And this is where, you know, since I only talked about regular graphs, I did not have the problem that came up during several talks about breaking vertices, right? Because if you have breaking vertices, this is more ideals that you get that is not sort of given by the connectivity of the graph. So there's a subtlety there that is not a problem for the regular graphs. And it seems to me that it shouldn't matter for these conjectures that I have sort of showing here, but they certainly matter for, you know, the proofs. So I'm not sure I'm answering your question, but I mean, there is of course you need to understand the since you're trying to encode the graphs in a C-star algebra, you need to understand the ideal structure of the C-star algebras in order to say something about the graphs. But it turns out, and even, you know, this perhaps I should point out over here, that, you know, there's also a richer ideal structure of the fixed point algebra, which comes into play here when you're then working with the gauge action.
Yeah, but you see, when you look at the property of being saturated, yeah, you can just express it for graphs, but it doesn't make any sense in a purely graph theoretic way. You need to talk C-star algebras. And then I fully agree with you, this is caring about ideals and how it works. But the property of being hereditary is important regardless of any graph algebra.
Right. Yes.
So I was amazed. It was just a question during my lecture course. Is it really topological, this definition of connectedness? Actually, the question was, do hereditary subsets form a topology? And to my astonishment, yes, they do. And even my further astonishment, the connectedness in the sense of a hereditary topology is exactly the connectedness in views.
Right.
Yes. Okay, but it was not an important question.
Okay, so any other questions? Well, let's
Thank you.